So as I anticipated a little bit the talk of Pierre, I tried to put my presentation in a different perspective, which is actually not so much about our ERAM observatories, a little bit, but not focused on it. But on the general landscape, you can roll out in the next 10 to 15 years for ground-based submillimeter and millimeter radio astronomy. And I should also add from a non-dreaming perspective, I would like to give you a couple of hard facts. And let me just start with classifying a little bit and reminding you the current and the planned observatories as much as I know about it. The existing facilities is divided in basically 3 classes. There is a quite a substantial number of 10 to 15 meter single dish facilities, as you can see in this list. And I added the ALMA total power antennas to that. That has its importance to keep the community really active with their own projects. But some of these 10 to 15 meter single dish facilities have also specific targets like SMT, which is mostly cosmology targeted. Then we have the 3 observatories which are in the 30 to 50 meter diameter single dish class. Those are at the current day mostly millimeter and short submillimeter facilities. The IRAM 30 meter telescope is probably going to the highest frequencies and will be upgraded in the near future to really serve with good efficiency up to 350 gigahertz. For the 45 meter telescope in Nobeyama and the LMT, this will be much more difficult. Then, of course, there are the currently operating interferometers, at least for the big ones. Pierre has said basically everything which has to be said. I should add, SMA is a very valuable test bed for technologies and also for performing non-luminosity limited observations in the long submillimeter range. Okay, let me then look a little bit what is known about land facilities, and I really repeat, this list is potentially incomplete. We have on the 10 to 15 meter single dish side still the Yama project, which has been stalled for a couple of years, but I hope they can continue soon. This is AMA type telescope or APEX type telescope in Argentina. We have then the AMT, the African Millimeter Telescope, a project which is pushed by a Dutch group in Radboud, mainly to do EHT, VLBI observations, but also to do eventually survey work at shorter millimeter wavelengths. And then I added to this, although it's a smaller thing, but the imminent arrival of CCAT Prime, which is a survey instrument with smaller diameter, but with a huge field of view. On the 30 to 50 meter single dish class, we have converging projects from Europe and Japan, and maybe also from US. These things go up and down, at least in US. The most advanced is, of course, the project planning for Atlas, which you will hear in the next talk by Claudia. Those projects basically tend to increase the frequency range of the 30 meter to 50 meter class into the sub-millimeter range, and therefore they have to be placed at a high side. I should add, this is by no means, those are by no means simple projects. Actually, whatever people tell you, those are very difficult projects, because to make 20 or sub 20 micron surfaces across across such a big dish is exceedingly difficult. And also you have to be very clever how to manage wind and weather. And then we should not forget, and Pierre didn't talk about this, that there is a project called the Next Generation VLA, which will impede or step into at least the lower part of the millimeter range in terms of frequency coverage, which will really be much bigger in a collecting area. And of course, this is not yet decided and it's far ahead, but we should not forget about this. Okay, let me then explain you a little bit the technical frontiers. There are trade-offs to be made within, and the estimated timescales for substantial progress on, as I see it from my side. And there is first, again, the development of this larger, higher frequency single dish telescopes. There will be a trade-off with the field of view to be made. And I think we should not expect this thing be on the sky in less than 5 years. Although some companies tell you, of course, the opposite. The most low-hanging fruit is the receiver bandwidth, including multiband observations, and I think you have heard about this also from Christoph's talk. There has been, of course, there has to be the inclusion of the corresponding backends. And you have to be very careful in not losing what you gain with bandwidth by increasing the noise performance or degrading the noise performance. But these things will happen on very short time scales, at least for the IRAM telescopes and also for the smaller observatories. Larger continuum focal plane arrays. So the including multiband and low resolution options. These include the NICA 2 upgrades, some new instruments like the Espresso, which will be also presented in this workshop, using a Martin Paplet interferometer. And then if you believe what technologists tell you, you might expect that in a couple of years you have multi-wavelength pixels, which you can use as a low spectral resolution detector. All this has a very broad time scale. The first improvements will certainly come in the next 2 years. And then the dream projects will certainly need much longer time, as some of the persons responsible predict. I guess that the next step for number of pixels will be not before 5 years, if you take NICA 2 or SCUBA 2 as a baseline. Heteroentire multi-beam arrays are, of course, for single dish telescopes are, of course, existing already, but the next generation is already in preparation. Those are very complex instruments, I should say, and therefore they will not be compatible with or or at least not easily be compatible with multi-band approach. So you will have at one time only probably one band to survey. The instantaneous IF bandwidth is still to be discussed, but everybody hopes that these things go on sky in the next 3 to 5 years. So Pierre has touched on this a little bit. Multi-beam for interferometry is a so-called holy grail for the interferometrist. And I will come back to this in a moment. Those things are extremely complex, and I would say for a system like ALMA, just don't ever think about it, okay? This is a no-go if you have more than 10 or 15 antennas. The bandwidth is a problem to be traded off. You cannot imagine that you have the maximum bandwidth you have with single pixel receivers, and the same is true for multiband. What I can offer you is the first systems working on a 10 years timescale if the money for this pretty big projects is available. Backend developments, correlated developments, and autocorrelated developments are increasing quite quickly due to the increased speed in electronics. And this means that the number of channels in a given bandwidth will also increase by will deliver you a higher resolution spectra. And those are progresses which are available on fairly short timescales of years. Finally, angular resolution indeed can potentially be increased by 2, 3, or even 5 through a limited number of outlier stations if you accept sparse imaging. I do not believe that the imaging quality requirements which have been set for ALMA will ever allow you to fill the apertures with the same signal to noise as you have today for baselines which are 2, 3, or 5 times bigger. But at the same time, I should say this is not always necessary. The ALMA specifications are really very constraining, and for many science targets you can relax that, and there is also great progress on technology of sparse imaging. So this is a direction where one should look at, both for ALMA but also for NOEMA. And of course, that needs more money and technology to transfer the signals over large distances. I will not talk about polarimetry, time variability, and other things which are already in preparation or existing, because that would be too big for today. So what are the direct consequences? The collecting area will not increase substantially over the next 20 years, with potential exception of the NGVLA program in the 3 mm range. Some telescopes will increase efficiency and throughput. Single line, single point source sensitivity will thus not substantially increase for the next 2 decades. Continuum single source sensitivities will possibly increase by factors of 2 or 4, also depending on the availability of the SED models. But what I mean there is, with the increased bandwidths and the developments in the continuum detectors, you can hope that you increase the sensitivity by this amount. And of course, if you know something about your spectral index, you can add bands together in an efficient way, which gives you an extra advantage. Where we will see big increases is in mapping speed for single dish and line and continuum. And those are the numbers I would propose you, 50 to 100 for line work, and probably as compared to Nika or Scupa 2, still a factor of 50 to 100, where you fold in sensitivity and number of pixels. On the interferometry side, we will see less increase in mapping speed, but still factors of 10 and more, both in line and continuum. Frequency survey speeds will see also important increases by a factor of 4 to 10, with an additional benefit of high resolution coverage. And this is very important because it means that your data throughput or output is up by a factor of 100 or more. And last not least, I should mention, even though PCMI is not really a community which is very much concerned about this, but millimeter VLBI will become more sensitive and allow to observe new targets. Okay, what does that mean for the science? Of course, you can make deeper continuum detections and instantaneous continuum slope measurements, much bigger and deeper continuum maps, which will result in bigger source samples, and I will give you an example. Broadband and frequency survey observations with increased efficiency, multi-line and therefore multi-line analysis, and Pierre has touched on this for the extragalactic work, will really become essential to make maximum use of the spectrum to understand the physics and chemistry. This is only at the beginning of its path, and this community should take it really serious to make all efforts necessary to gear up the speed. Because we cannot easily increase line sensitivity, stacking approaches in continuum, both in continuum frequency, using big maps or frequency scans will be increasingly important. And I said outlier stations for protoplanetary disk structures on the AU scale in low frequencies will be quite efficient if you get the money and the technology to peek into the otherwise optically thick disks at these scales. This has been identified as one of the major in JVLA science cases. Evolved stars and AGNs will also profit from that. And then VLBI with its new structure with many more participants in the millimeter and sub-millimeter range and the increased bandwidth will eventually find the possibility to go back to maser observations and eventually also line absorption techniques in front of AGNs. So let me give you a couple of status on the technical developments. Here is the receiver bandwidth. We have today 8 gigahertz dual pol for ALMA and 16 gigahertz dual pol for NOEMA. Tomorrow we will have in very likely, and we have it already at the 30 meter for heterodyne work with EMIR, 32 gigahertz dual pol, and NOEMA will have this dual band capability as of 2023. And then there is, and Christoph has mentioned this, work on the next mixer generation, which will still double this in the next, let's say, 5 to 7 years until it comes to the telescope. And their backend is, of course, a critical path on the critical path with higher frequency sampling rates and also power consumption, which has to be managed. Let me give you an example here of this dual band upgrade at NOEMA, where you can see at the bottom the dichroic, which is in the worm and which basically helps you to, or allows you then to observe at the 1.3 and 3 millimeter band at the same time. This not only gains observing speed, but also a lot of new possibilities for atmospheric phase calibration. In order to allow the single band observations in the future, also in the future with highest sensitivities, you can retract this system to a large degree and receive the original performance of the receiver channels. So this is a system which is already prototyped and will be gradually extended to equip all antennas. There's, in addition, and probably as Christoph mentioned as well yesterday, explorational development ongoing to put this band combination into the cryostat to reduce noise penalties.
2 minutes, Karl.
How much?
2 minutes.
Okay. So let me give you at the end a couple of examples, what it means to make these big maps in different lines. This is a very good collaboration in France, which most of you have seen, to map the Orion's cloud. Then NICA 2 is very active and has made breathtaking galactic maps, which you can see here, and they are so big that you cannot really appreciate the quality, and only if you zoom in and you see here a result from NICA 2 in the same map as compared to other wavelength ranges and other instruments, you appreciate that you open up a new window to detect star forming sites in the galaxy. Large scale extragalactic nearby galaxy mappings is, of course, depending on how fast you can map, and there will be, as I said, rapid progress in mapping speeds. This is another example of M82 mapped, which is totally impossible to think about in the previous years, but now ALMA and NOEMA can do this kind of things with resolutions which approach more and more the size of GMCs. Okay, let me say a word to Westerbork, to multi-beam interferometry. You have to understand that this is an exceedingly difficult technology, and a good example is the Westerbork operative system, which works at the H1 frequency. I should say that direct transposition to millimeter wave interferometer is very challenging because the antennas are differently mounted. So you have to take into account the field rotation, and you have to manage very well the on-the-fly method before you can ever think about this. And also in this respect, you would probably not do phased arrays, but simple classical multi-beam receivers. I will hop on to the question of multi-line observing. This is very important for all our developments, be it ALMA, NOEMA, or other observatories. You see here an example of Hot Corino, where you more and more can use software to line identification in a quite efficient way. But as you see in this example, there are still lines which are not very well modeled and or even not explained. And this will be very interesting in the near future. So I jump over the VLBI and go directly to my summary. There's still to be a lot discovered with the current sensitivities. However, the community should prepare to use the next dimension of large data sets, large multi-line and continuum maps. And this means that you cannot do these things in the future with 2 people or 3 people. We have to learn how to set up larger communities and collaborations. Many features will be added in the next years. Field is still dominated by the cold ISM research, but you should be aware that other applications, VLBI, non-thermal emission, Sunyaev-Seldovich science, and a couple of other things like pulsars will become more important in the future. The timescales of most larger developments are in the 5 to 10 year range, and you should not burn PhD students on things which are not well defined. So please be careful. ERAM is working intensely in almost all fields, and with increased speeds, will increase speeds through increased number of collaborations, and this is particularly true probably in the data business. Thank you for your attention.
Thank you, Karl. There is a question by Nicolas.
Yes, my question is probably more relevant also to the previous talk. It's because I know that Noema is doing it. It was just if you can expect some. It's not necessarily actually a hardware development, but some implementation on autocorrelation modes in large interferometers. I mean, like a single dish mode with the 50 antennas of ALMA or so in the next future, because some source may require not necessarily big maps, but sensitivity on just a single pointer.
Yeah, there are several modes which are going in this direction. One mode is the phasing mode, so to speak. But it's true that this is used for the VLBI observing. What we do not have, and I should admit, is autocorrelation mode, which gives you a signal for each individual antenna, which you can add up in the follow-up. I'm not sure whether this would be very efficient for all applications, because these systems are not set up for maximum single dish stability, and many things which you see in this single dish work are cancelled out by watch switching and so on and so forth. So if you want to really profit from such a mode in an optimum way, you have to basically take care of things which in interferometry so far have not been taken care. So yes, in principle, this is possible, but it would need considerable work, I would say.
Karl, yesterday there has been a suggestion by one of the speakers, and I think it will be made again in coming days, to have that ERAM observation in the 50 gigahertz range.
Yes. We have thought about this in a very preliminary way. This would need basically new receiver space, which we have in the cabin, but it has to be traded off against future projects of multi-beam. We probably do not have the space for both.
So thank you, Karl, for your a great talk, which was back to Earth, I would say. And there's one point I wanted to stress, and I was happy that you made that point, is about the continuum and the fact that with the very broad bandwidth, you have a sampling of the continuum, particularly with NOEMA, that is incredibly fascinating and provides a lot of constraints on the SED. I mean, that's one thing I discovered in the large ZGAL proposal, is that project, that for all the sources, we have very good sampling of the continuum. And in some cases, we also see the turnover in the radio for the AGNs. So I think there's a lot of things to be done there, and particularly in the study of the dust properties, and as Ambra explained yesterday. But the currently available NOEMA bandwidths is a wonderful tool to do that. So I just wanted to stress that.
Yeah, thanks. Yeah.
Okay, thank you again, Karl.